I'm going to talk about some joint work with Rohan Goyal, who is now a grad student at MIT, Prahladh and Ashutosh, who are both here. As the title of the talk suggests, this is a coding theory talk, right? And there's decoding univariate multiplicity codes. Right? But some of the questions at the heart of this work are, I think, have a broader context. Even outside, they have a life outside coding theory. They're important for coding theoretic reasons, but they are interesting questions to study on their own. And I'll sort of take that view for the talk. I could have retitled the talk as Fast, Noisy Hermite Interpolation, but I was afraid of being booed by a coding theory audience. Okay, so let me start. Please stop me and ask questions that come up. I have a lot of slides. I'm happy to not cover all of them. So let's start with the question of noisy polynomial interpolation. So the setup is that we have an underlying field F. We have a set E of evaluation points of size n, and we have a function R from the set E to the field F. And we have talked about this multiple times, using the fact that no two distinct polynomials of degree D can have too many agreements. It's easy to see that the number of polynomials P of degree at most D that agree with the function R on greater than n plus D over 2 points is at most 1. So there's at most one such polynomial. And the kind of questions we will be interested in will be of the following flavor. So given the set E and the function R, find P efficiently. And this is the question of noisy polynomial interpolation. If R and P agree everywhere, this is polynomial interpolation. And we are asking for agreements at only a sufficiently large subset, so it's noisy polynomial interpolation. This problem has been studied for a while. So there are many known algorithms. Since the 60s, Peterson's algorithm, Burley-Camp-Macy's work, Burley-Camp-Welch, which is relatively recent. These are all very elementary algorithms, but they're neat and pretty in their own right. And they are very, very useful, certainly in coding theoretic context, but also elsewhere. This talk is going to be about generalizations of this problem, and we are going to look at generalizations on two fronts. So we will look at the setting of higher multiplicities. I'll say what that means, and we'll look at the setting when the number of agreements is much smaller than n plus d over 2. So let's start with the case of high multiplicity. So here's a definition. So polynomial P vanishes with multiplicity at least S at a point A if P and all its derivatives of order at most order less than S are 0 at A. Throughout this talk, think of the field F as being of sufficiently large characteristics, and we will just work with standard derivatives. It's not important. Okay, so this is a generalization of the fact that we saw on the first slide. So a non-zero univariate polynomial of degree D over a field has at most D over S zeros of multiplicity S. This is the fact that leads to univariate multiplicity codes having good distance. Okay, so a consequence of this is, again, we are back in the previous setting. So now we again have a set of n evaluation points over an underlying field, and now we have a function R that maps E to F to the S. So the image of R is an S tuple over the field F. And then the number of polynomials of degree at most D that agrees with the function R with multiplicity at least S on greater than n plus d over S over 2 points is at most 1. This is a consequence of the fact that we had last. Now, if you set S equals 1, we are back in the regime of noisy polynomial interpolation. By the way, so agreement with multiplicity S just means that, so R of A is an S tuple. We should think of that as the evaluation of P and all its derivatives of order at most S minus 1 at A. So noisy Hermite interpolation is a question of, given the set E and the function R as input, you would like to find this unique P efficiently if it exists, or say that there is no such P. Okay, great. So now, so this is the setting of multiplicities. Now let's go and talk about the setting of tolerating more errors. So now, if the number of agreements is less than n plus d over S over 2, we know that the close enough polynomial may no longer be unique, but one could ask how many can there be? And an old theorem of Johnson that says that the number of such polynomials is going to be at most square root of n d over S. Johnson's theorem says more and much more, but this is what it says in this context. Okay, so there aren't too many such polynomials. There's more than one potentially, but not too many of them. So we can ask for algorithms that maybe find all of these polynomials efficiently. And that's what we are going to do. So this is again a problem that has been well studied. So if you look at noisy polynomial interpolation, so this is the S equals 1 case, then we have very famous algorithms of Madhu and Venkat and Madhu from the 90s that give polynomial time algorithms for noisy polynomial interpolation up to the bound that Johnson's theorem mentions. And immediately after these results, there were subsequent attempts at improving the running time of these algorithms. So algorithms in Sudan and Guruswami Sudan are polynomial time, maybe n cube time, roughly. And there are a couple of papers in between that I'm not mentioning here, but in early 2000s, Aleknovich showed that you can actually do most of what Guruswami Sudan do in nearly linear time. And this most is because Aleknovich's algorithm works epsilon up to epsilon close to the Johnson bound for any epsilon greater than 0. Guruswami Sudan works up to the Johnson bound. So that's the only difference. So Aleknovich's algorithm should be thought of as a nearly linear time analog of Guruswami Sudan's result. All right. So now let's switch back and talk about Hermite interpolation, noisy Hermite interpolation up to the Johnson bound. So in 2001, Nielsen showed that we can actually do for arbitrary S, we can do noisy Hermite interpolation up to the Johnson bound in polynomial time. This builds upon the ideas that were there in Guruswami Sudan's algorithm and a few more ideas on top of it. However, unlike the work of Aleknovich, which gave a nearly linear time analog of this question in S equals 1 setting, we didn't have near linear time implementations of Nielsen's algorithm for a while. And then in a survey in 2014, Swastik asked if there's a nearly linear time analog of Nielsen's algorithm. So is there a nearly linear time algorithm that does noisy Hermite interpolation up to the Johnson bound? Okay, so we will get back to this question. This is the question. This is the question of interest for us. But let's briefly talk about what happens beyond the Johnson bound. Why would we stop at the Johnson bound? So for noisy polynomial interpolation, the setup of what happens beyond the Johnson bound is unclear. So we know that the answer to this question depends on the set E of evaluation points to an extent. We don't know algorithms. So yeah, there are many nice open questions here. Papers come out every few months, including with people in the audience. For noisy Hermite interpolation, in 2013, Swastik and around the same time, Venkat and Carol Wang, they gave algorithms that are of the following flavor. So for all sufficiently large S, depending on epsilon, there is an efficient algorithm for noisy Hermite interpolation over fields of characteristic something for agreement greater than 1 plus epsilon times D over S. So this is much larger than square root of ND over S, which was the bound in Johnson. And these are polynomial time algorithms that will find all polynomials with agreement at least 1 plus epsilon times D over S with a given function R. Note that D over S is necessary here. We are trying to find a degree D polynomial, and every evaluation point sort of gives us S independent pieces of information. So we need at least D over S. And this says that for an arbitrary epsilon, if S is sufficiently large, then we can do 1 plus epsilon D over S. Now, before this result, it wasn't even clear that the number of such polynomials is small. This is far beyond the setting of Johnson's theorem, and we don't know if the number of such polynomials is small. And this is the result that Sashank mentioned in the previous talk. So Swastik, Shubhangi, Nogar, Ranzui, and Mary Wouters later showed that the number of such polynomials is actually a constant, and this constant has seen subsequent improvements, including the results that we saw in the last talk. Okay, so now because of these results that show that the number of such polynomials is a constant, we know that the output size of these in these problems is linear in the input size. So one could ask, can we compute all of these polynomials in nearly linear time? Without a list size bound, this question doesn't make sense because maybe the output size is super linear in the input. So one has to tailor it appropriately. So the question we will be really interested in is to understand if this theorem can be, if the algorithm in this theorem can be done in nearly linear time and not just polynomial time. Yes. Yes, we think of epsilon as a constant. Yeah. All right. So this brings us to our theorem. So we show that for the same setting of parameters as before, there's a nearly linear time algorithm for noisy Hermite interpolation with agreement greater than 1 plus epsilon times d over s. Okay. So that's the theorem. Questions? Okay. So there's some caveats that I should point out. One is that we need epsilon to be a constant. We need d over Sn, the rate of the underlying univariate multiplicity code, to be a constant. The rate issue is also an issue with Aleknovich's result, which is only nearly linear time if the rate is a constant. Yeah. So the other issue is that the characteristic of the underlying field should be sufficiently large. Here also, I think the problem is more fundamental. We don't understand some of these problems when working over fields of small characteristic, even without the near linear time aspect of these algorithms. So Swastik's question was whether we can do this. We can do noisy Hermite interpolation up to the Johnson bound in nearly linear time. So this answers that, but in fact, with agreement significantly smaller than what Johnson promises. So this is an analog of Aleknovich's result, but now we are in the setting when S is greater than 1. In fact, all of this requires S to be somewhat large compared to epsilon. And yeah. So we don't know. So if we make S 2 or 3, we can. We do. So for Johnson, yeah. In fact, if you want to get to Johnson bound for all S, we get nearly linear time. The algorithms are slightly different, but same techniques, similar ideas. Okay. Any questions so far? Yeah. Great. The algorithm is randomized, and it is randomized for the reason the part of the algorithm that's randomized is the part that Shashank talked about. This is this question of getting a small list eventually. Other questions? Yes. Yes. Oh, I should have. No questions so far? All right. Okay, so in the remaining time, let me say something about the proof. Let me at least talk about the high level ideas in the proof. Okay, so the algorithm builds on ideas in prior work, and in particular will rely on the polynomial method, which is at the heart of Sudan's algorithm and Guruswami Sudan's algorithm, all the list decoding algorithm for algebraic codes in between. Here again, there are a bunch of questions that we ought to answer. How many such solutions can be? In general, if you look at it carefully, this is just a linear system, and so it can be solved in polynomial time, and this is what Guruswami banged did. Okay, so is the sketch okay? So I want to say a few more things about the details. Are we good so far? Questions? Yeah. We can. Q is linear. In fact, Q will be in the monomial basis. Other questions? Okay. Okay, so our goal here is to construct a differential equation, in fact a polynomial Q of this particular form. Q is linear in Y, has high degree in X, such that this holds. And we know how to do this in polynomial time by solving a linear system. But we will rely on an approach of Aleknovich to do this faster. So let me try to show you a little bit of how this is done. So let's say that the set E is alpha 1 up to alpha n, and R of alpha I is this S tuple, so beta I 0 up to beta I s minus 1, and m less than s is a parameter. Okay, so I'm going to define polynomials u0 up to um of degree at most n times s. So this should be n times s. okay, such that u satisfies this property. So the kth derivative of ui evaluated at alpha j is beta j comma I plus k. Let me say this in picture. So u naught is the unique univariate polynomial of degree less than n times s, such that at alpha 1, beta 1 0 is its evaluation, beta 1 1 is the evaluation of its derivative, beta 1 2 is the evaluation of its second derivative, and so on. So this column here is the evaluation of the first s derivatives of u naught at alpha 1. u1 is again defined similarly. So if you look at, so we throw out the first row, and the remaining column is the evaluation of ui and all its derivatives at alpha I. So these are interpolation conditions. We can find polynomials ui's with these properties. The degree will never exceed n times s because that's the number of constraints we are imposing. Is the definition okay? Okay.
You're thinking of u1 as the derivative of.
We are sort of thinking of that. So that will be clear in a moment. Okay, so suppose we got our hands on these ui's. So what's nice about them? What's nice about them is the following fact. So suppose p is a polynomial such that p and r agree on the input alpha I. Okay, then which means that p of alpha I equals r of alpha I, but r of alpha I was the same as u naught of alpha I. So p of alpha I equals u naught of alpha I. But not just that, something more general is true. The agreement of p and u naught was the polynomial that interpolated on the values and the derivatives. So if p is a polynomial such that p and r agree on alpha I, then p and u naught agree on all their derivatives up to order s at alpha I, which means that, so the statement just means that x minus alpha I to the s will divide p minus u naught. Similarly, x minus alpha I to the s minus 1 will divide the derivative of p minus u1, and so on. Okay, and we do this, so these are the kind of equalities we are going to get as a consequence of the structure of u and the fact that p has an agreement. Great, so our goal is to find a q. Okay, but now we are in the setting when we have these ui satisfying these nice properties with polynomials in the list. So now let's consider a polynomial q of the form y naught minus u naught times h naught plus y1 minus u1 times h1, etc., etc. hi's are for now arbitrary polynomials in x. Because of the relations between p and ui's, if p has an agreement with r at alpha I, we have the following property. We have the property that q of, if y naught is replaced by p, y1 is replaced by the derivative of p, and so on, then this polynomial is divisible by x minus alpha I to the s minus m. So one way of seeing this is, remember that if p and r agree on alpha I, then p minus u naught is divisible by x minus alpha I to the s, p prime minus u1 is divisible by x minus alpha I to the s minus 1, etc., etc. The m minus first derivative of p minus um is divisible by x minus alpha I to the s minus m, and that immediately gives this. Great, so this is about agreement at alpha I. If agreement happens on alpha 1 up to alpha t, and alpha i's are distinct, then by a simple Chinese remainder theorem, we get that q of x comma blah 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 is 0 mod this product. And at this point, yeah, I mean, if we can argue that the degree of this polynomial is not too large, then in particular it's less than t times s minus n, then the only way this equation can hold is that this polynomial must be identically 0. So the only thing needed so far in order to get this conclusion is that q should have low x degree. If q has small x degree, we can put a bound on the degree of this composed polynomial, and then everything will follow through. Great. So we are looking for a polynomial of this form. hi's we are free to choose, and we want to ensure that overall the x degree of q is small and q is non-zero. So the way to do this is to think of, look at the lattice generated by the polynomials y naught minus u naught, y1 minus un, so on, ym minus um, over the ring f adjoin x. So we are looking at fx linear combinations of these guys, and somehow finding a polynomial q with low x degree here can be phrased as a question of finding a shortest vector in this lattice under an appropriate norm. The result of Eleknovich that I mentioned earlier gave a general purpose algorithm for this problem. Okay, and the lattice here is very special. The dimension of the lattice and the ambient space are both a constant, so they come from M. And the degree of the generators of the lattice is at most n times s. This was the bound on the degree of ui's. And if we look at Eleknovich's algorithm in this setting, all of this can be done in nearly linear time. So we construct ui's, we look at the generators of this lattice, we feed it into the algorithm that Eleknovich gave, and what we get is a nearly linear time algorithm to construct q's. So that's the first, that's the construction of q. I have a couple of minutes. Oh, I have 5 minutes. Okay, great. So let me say something about the second part. So remember, the first part was constructing a differential equation satisfied by every p in the list. The second part was to solve this differential equation. So so what we are looking for is solutions of equations of the following form: some a0 plus a1 times p plus a2 times p prime, and so on and so forth. Clearly, the solution space is it's an affine subspace, and Guruswami and Wang argued that the subspace has dimension at most m. And they gave an efficient algorithm to output a basis of this subspace. Our main technical statement for this part is it's a fast algorithm, it's a nearly linear time algorithm that takes the polynomial q that we constructed in step 1 as input and outputs the basis of the solution space of an equation like this. Okay. So I can say a few more things in a couple of minutes. So let's just look at the m equals 2 case for this discussion. So we are looking to find p's such that a0 plus a1p plus a2p prime is 0. In fact, let's ask the simpler question. So we would like to do all of this, construct a basis of the subspace containing such p's in nearly linear time. But let's even drop the derivative and ask, can we find a p such that a0 plus a1p is 0? Can we find this p in nearly linear time? And if a solution exists here, it's clearly unique, right? If there is such a p, then it must equal negative of a0 over a1. So we can always do long division to find such a p, but can we do this in nearly linear time? This is known. This has been known for the last 50 years, but it's not trivial. So these are results of Steve King, Kung, Strassen's sequence of papers in the 70s. These algorithms are based on applications of fast Fourier transform, but they are very, very important results. They introduce ideas like Newton iteration, variants of divide and conquer that we have been using for the past 50 years in computational algebra. So let me give you a flavor of what this algorithm looks like. So the way we will try to find this p is so p is a polynomial of degree d. We'll try to find the first d over 2 coefficients and then the last d over 2 coefficients and do it separately. So we'll decompose p as u of x. This is the part of p of degree at most d over 2, and v of x, which is the part of p of degree greater than d over 2, greater than or equal to d over 2. For p to satisfy this, let's try to understand what conditions u and v have to satisfy. So we plug in p equals this, we rearrange, we get this. Now, if you stare at this expression, notice that this part, a1 times v, comes with x to the d over 2. So this part is only going to output monomials of degree greater than d over 2. Which means that if this equation has to hold, if this has to equal 0, then a1 times v, so all the monomials of degree less than d over 2 come from here. So it better be the case that a0 plus a1u is 0 mod x to the d over 2. Okay, so this is the monomials of degree less than d over 2. If we focus on monomials of degree greater than d over 2, some of them come from here and the rest comes from here. So what should hold is that b of x plus x to the d over 2 times a1 times v should be 0 mod x to the d, where b is just a0 plus a1u. We know a0 plus a1u is 0 mod x to the d over 2, so it only generates monomials of degree greater than d over 2, and so each of these conditions should hold. And for a correct u, if u is correct, then b is divisible by x to the d over 2. So in fact, we can refine it further. We can replace this b by some b tilde which is b over x to the d over 2, and can take out d over 2 from all sides. So what you get is b tilde should satisfy b tilde plus a1v is 0 mod x to the d over 2. So there are two conditions. A naught plus a1u is 0 mod x to the d over 2, and b tilde plus a1v is 0 mod x to the d over 2. Okay, so u and v, if p, which is equal to u plus x to the d over 2 times v, has to satisfy this equation, then u and v must satisfy this equation. So this is like two equations of half the size. And if you stare at this carefully, you'll notice that everything we have done on the way is something that can be done in nearly linear time with FFT. So what we get is two problems of half the size together with some pre and post processing, all of which is nearly linear time. And we recurse and do this log n steps. We get a nearly linear time algorithm for solving equations like this. Great. Now let's get to equations like this. I'll stop in 30 seconds. So one of the issues in this case is that the solution is no longer unique, right? So now if we try to do what we did in the earlier case and try to decompose P into U and V and try to make this work, the non-uniqueness of solutions poses a problem. Recursively, we can't maintain, we can't try all possible combinations of UIs, VIs. So that becomes an issue. And in Guruswami and Wang's algorithm, they gave an efficient way of, so they show that the solution space is a linear space, and they get an efficient way of getting our hands on the basis of an affine space. And this basis is quite nice and natural in this setting. So what we do is we try to construct each of these basis elements one by one. And once we sort of identify what basis element we are trying to construct, we can reduce this equation to a different differential equation which happens to have a unique solution. So for every choice of basis element, we end up with a proxy equation which has a unique solution and where a divide and conquer type idea does work out. Okay, so that's not saying much, but but that's all I have time for. Okay, so let me end with some open questions. So one nice question that we haven't thought too much about is try and generalize some of these two multivariate polynomials. There are results on this in the differential equation literature. There is a coding theoretic motivation. This would be the question of list decoding multivariate multiplicity codes in nearly linear time. We don't know how to do this. There are some obvious technical issues, but they may just this may just be doable. And it'd be nice to understand the state of noisy polynomial interpolation. So this is the question of list decoding Reed-Solomon codes beyond the Johnson bound, including questions of efficient explicit construction of evaluation points for which we know that the solution size is small. We know such sets exist, but we don't have explicit constructions. And then eventually efficient and nearly linear time algorithms for decoding in that regime. Okay, sorry, I rushed through the last bit. If there are questions, I'll take them. Yes.
Okay. So you mentioned that your results only works for fields of very large characteristics zero. What is the fundamental?
So so even if we ignore the issue of finding nearly linear time algorithm, we do not know if univariate multiplicity codes are combinatorially list decodable up to capacity over small characteristic. So the problem is even at combinatorial list decoding level. And then, so we don't know that. We don't have polynomial time algorithms. So this would only come way down the pecking order, I think. So understanding. Yes? Yeah, it's the dependence that KRSW have. So 1 over epsilon to the 1 over epsilon. It's not poly 1 over epsilon. That'd be nice. Guruswami, Wang, is that clear? That's not clear to me. Yeah, it will be the same. It will be the same. So just a basis we can output in respectable running time with epsilon. Yeah. Yeah.
Do this at the end, you will have like D leaves in this recursion.
Right.
And D is also omega of n, right?
D is omega of n, yeah.
Okay. So
there are log n levels.
So you need to solve each of these leaves in just polylog time.
In fact, you can solve it in constant time because yeah, the degree becomes 0. Yeah. Other questions? Yes.
Are you familiar with this like Chinese remainder theorem code?
Yeah. Great. We have tried.
So Aleknovich doesn't give you a near linear time for that.
So it's not clear. So I'll say something incorrect now. It's been a while. But we don't know how to generalize. So in fact, I think we don't know whether Chinese remaindering codes are list decodable up to capacity. Do we know this? We don't know this. Yeah. Up to Johnson we know, but
Yeah, that was more my question.
right.
So there's this paper by I believe like Henry Cohn and
Right.
I'm forgetting, and they had
Yes.
this, like
Henninger, I
they
think.
use the same sort of idea.
That's true. So they reinterpret Guruswami's Sudan in this language. That's true. Other questions? Okay. Okay. Thank you.